In the world of chemistry, scientists spend decades asking one question: how much product can I make? We call this percentage yield. But today, that question isn't enough. In the modern world of limited resources and a climate crisis, we have to ask how much of my starting material actually ends up in a final product, and how much is becoming a waste. This is where atom economy comes handy. Welcome to Alchem. Today, we'll dive into atom economy, a pillar of green chemistry. Whether you're studying IB or Cambridge, mastering this concept is essential for understanding how modern industry balances profit with the planet. Atom economy is one of the latest concepts that is recently being added to the textbook and the syllabus. In other words, we are expecting to see at least one question in the final exam. This is a very simple calculation, so let's define what atom economy is. It is a theoretical measure of the amount of starting material that becomes the useful product. Unlike the percentage yield, we calculate after the experiment. Atom economy is calculated from just a balanced equation without carrying any experiments. So it's done by the ratio of the molar mass of the desirable product that you are trying to make over the total molar mass of every reactant, which is the raw material. And this determines the efficiency of the reaction and trying to minimize the waste product. Before we try real question, I want you to understand this using a logic. Yesterday I was making Greek yogurt because I like mine thick and creamy, but when I bought this Greek style yogurt, it wasn't actually Greek enough for me. So I've used 2 tubs of 1 kilogram Greek yogurt, dumped everything onto the cloth and tried to drain all the liquid out of it, and 8 hours later I ended up with Greek yogurt with lots of liquid that's drained out called whey. And the Greek yogurt was really thick and creamy as I wanted, and I only was able to harvest just over my size of my palm. And I measured this and I found out that I made 750 grams of this, and the yellow liquid, which I didn't bother to measure because to me it was a total waste. I didn't know what to do with it, but I'm assuming it's over 1 kilogram. But I don't need to know the mass of the waste product because I only want to find out how much his desired product is made. So the simple calculation of efficiency of homemade Greek yogurt. First of all, we put the mass of desirable product as a numerator, 715 grams, over the total mass of the raw material, which is 2 kilograms because I used 2 tubs of 1 kilogram. And divide those, multiply by 100, and that gives me the efficiency just over 35%. And now I understand why Greek yogurt at supermarket is more expensive than the normal one, because it takes time, it has lots of waste product, the efficiency of making is just over 35%. So if you want to make it yourself, just understand that you will get less than half of what you put in. In the yogurt making, I was using mass in grams or kilograms. But when it comes to atom economy, it is important that you use the molar mass. This is because if you use more reactants, of course, more product will be formed, and the increase in the production will be directly proportional because of the law of conservation of mass. So technically, you will get the same answer, but for the convenience, just use the molar mass because all you need is a periodic table and a balanced equation, and maybe you need a calculator too. Let's calculate the atom economy. So this formula of atom economy is not going to be provided in the data booklet or data sheet. So you either need to memorize this or understand how it works. So let's take a look at this equation, production of urea. The name urea came from the urine because this is the compound that's discovered from the urine in 17th century. And this became a pivotal compound that built the foundation of organic chemistry in the 18th century. So here, urea will be the desirable product, and those two, phosphogen, COCl2, I normally call this cockle, with 2 moles of ammonia will be the reactant as a raw material. And HCl will be the byproduct because this reaction is not to produce HCl because HCl can be produced in many other equations. So this is a waste in this case. Let's go through step-by-step calculation process. Step 1, make sure that equation is nicely balanced. And this equation is nicely balanced for you. Step 2 is crucial. Calculate the molar mass of a desirable product, which is the urea, right? So have a look at your periodic table, get your molar mass. So if you are using carbon as 12, make sure you use whatever the value that states in your data sheet. For IB, it's clearly stating as 12.01. For Cambridge, it'll be the same case. And it's a relative molar mass, so you don't need to have units. And step 3, this is where a lot of mistakes are made. Calculate the molar mass of all reactants here. So for the COCl2, very easy. But for the second one, this is where the booby trap is. Calculate the molar mass of each ammonia, just like the way that you normally do, which is 17.04. But this needs to be multiplied by the coefficient. So we got 2 in front of the ammonia. So make sure you multiply the molar mass by 2 for the ammonia, and adding the molar mass of both reactants will give you the total value of the denominator, which is 132.99. Now step 4, atom economy. Using the formula above or in the previous slide, the mass of the desirable product, which is the urea, over the total mass of the reactant times by 100 will give you 45.17% atom economy, meaning about 53 or 50 or 55% will be the waste product. Before we try next question, there are some important exam tips for you. Take your time. Do it slow. Do it carefully. This is one of the simple and easy questions, but not many students will get the full mark because they make regretful, careless mistake by adding, numbers wrong or rushing, or try to calculate everything at once. So calculate the numerator and denominator separately. If you slow down your calculation process by 30 seconds and do it carefully, you can save 2 to 3 marks. And number 2, check whether the equation is balanced correctly first. This is the only time where the molar mass is multiplied by the coefficient. Other mole calculation, you don't multiply by the coefficient, but atom economy does. So make sure you do that. And number 3, use the periodic table even though you know the molar mass of oxygen is 16, but it'll actually say 16.00 in the periodic table. So just double check, hydrogen is 1.01 instead of 1. Have your periodic table in front of you. Make sure to check the value before you calculate the molar mass. Are we ready? Let's implement all the tips and know-hows from the previous slide and calculate the atom economy for the following equation. So first tip is to balance the equation. You can use whole numbers or fractions or decimal places, but I strongly recommend you use the whole number to make the calculation easier to avoid any careless mistakes. So I'll reveal the answers slightly later, so I want you to have a go. Second hint, identify the desirable product. So some of you might find, how do we know which one's useful, which one's a waste? In this case, we got 2 products, one's iron metal and one's a carbon dioxide. So CO2 is a waste here because there are so many other equations that could produce CO2 as a byproduct. And what scientists are focusing is not to produce too much CO2, obviously because of the global warming issue. So this is the equation where iron will be the main product for the use of iron steel to make something that's iron related product here. So make sure you know how to find the correct desirable product. So feel free to pause the video and check your answers after you're done. But be mindful, as an expert myself, I actually made a careless mistake using calculating atom economy for this one because I had a fat finger moment where I pressed 6 instead of 3 on my calculator. So just be mindful, even I done this many times, I could still make a mistake, and by taking it slow and carefully, you'll be fine. So you'll do better than me. So check your answers in a minute. Are you done? So here's a balanced equation. State the equation for the atom economy and check your values carefully. You can pause again and check your calculations, but note that the second equation, I show the full step of how to calculate the molar mass, multiply by the coefficient here, and finally got the total value of the numerator and denominator right. This is where you score the point. And then lastly, we have atom economy of 45.83%. And since we are using the molar masses from the periodic table or any other given data resources, the rounding is not really significant here. So you can round them to 1 dp or 2 dp, and sometimes the question itself will reveal and ask you to round into certain significant figures or decimal places. So you can actually round accordingly. The higher the atom economy, the better the efficiency of the reactions. But there are some reactions that have 100% atom economy. First one is an addition reaction where it deals with alkenes or alkynes that are unsaturated, containing C to C double bond or C to C triple bond. And when those multiple bonds break to add two or more new atoms, and it's called an addition reaction where we get 100% atom economy. And this includes addition polymerization where little monomers join together to form a long chain molecule, which is quite important for plastic manufacturer. So this one has 100% atom economy. Second example is combination reaction where elements are combined together to form products. So I've listed all, not all, actually a few examples of combination reactions here. Mg plus O2 gives you MgO, iron plus S gives you FeS, and some of them have a small subscript of 2s and 4s and 6s, depends on the charges and how the oxidation number works. But all of those examples have one thing in common, meaning they all produce one product. There's no byproduct. There's a single sole product. Doesn't matter the coefficient, but it just produces one type of substance as products. To summarize, high atom economy indicates less waste being produced, so the reaction is becoming more sustainable. This is very important where we approach for the green chemistry to utilize the raw material as efficiently as possible. Second, addition as well as the combination reaction have 100% atom economy because there's only one product. No byproduct is produced, but substitution, elimination, any other acids and bases, any other reactions that will have byproduct will have lower atom economy. So in the next video, I will go through the difference between percentage yield, percentage error, and atom economy because they are similar in a way but slightly different. So watch out for my next video and feel free to download the worksheet from the comment section because I have put some questions there for you to practice to prepare yourself for the exams. So knowing tips and know-hows, keep practicing, keep learning, and I'm here to help you as much as I can. So thank you for watching, and remember, you can do anything and everything. See you next lesson. Bye.